Hi everybody. Okay, so we're going to get started from by taking a look at what we did yesterday, a review, and then we will continue with the new section today. So please pay attention. Okay, alright, so review from yesterday in regards to Kepler's 3 laws, and we've got a video that we're going to be watching today after we're done our lesson. So Kepler's 3 laws, just to recall. Okay, first law we said was his understanding that all orbits are ellipses, number one. Okay, that's the first thing he discovered, with the sun at one focus and the second focus is an imaginary point. Okay, the second law of Kepler was that the sun will carve out equal areas okay, so when your object or your planet is furthest away from the sun, it is going slowest, so velocity is minimum, and we also said that EG here is maximum. Okay, yeah. Do you spend a lot more time? Yes. Okay, because you are going faster here, so you're able to cover more distance in that same amount of time. Okay, so this is D2. No, we did not say that. We did not say that. These are not related to summer and winter, correct? Okay. Summer and winter are related to the angle, the axis, where we're looking at the intensity of the sunlight that is hitting. So it's not about the distance from the sun, believe it or not. It has more to do with the intensity. Yes? The area is equal. A2 equals to A1. It just means the two areas are equal. Okay, for now, let's just keep it at that. It's more calculus based, so we're not going to explain that in that stuff. So yeah, time is equal. This time right here equals to this time right there. Yeah? We're looking at it just in terms of speed and how fast it goes and how we use energy to describe its motion. That's what we're going to be talking about next. Okay? So V is maximum here. And that's what we're going to do for this part of the chapter. Okay, and the last thing that we looked at for Newton's third law, not Newton, but Kepler's third law, was we said that the constant of the sun, Cs, which equals to R cubed divided by T squared, and of course we said R is in meters cubed and T is in seconds squared, which is also equal to big G, mass of the sun, divided by 4 pi squared. Okay, so this was Kepler's third law, and this was of course the constant of the sun. This is the constant of the sun. Okay, so this is what we did yesterday. Okay. Are we good? Let's erase this. And we'll start with the next section today, which is 6.3 from your textbook, gravitational potential energy. Okay, so 6.3, gravitational potential energy. All right, so I was talking about EG as being maximum when your object is furthest away from the sun, and EK being maximum when your object is closest to the sun. However, this EG, which we've been using since grade 11, we've been talking about EG as being MGH, mass, gravity, and height. However, we're talking about space right now. We're talking about the sun, and we're talking about objects that are really far away from the surface of the sun. So we know that G of the sun is not constant as you go further and further away. So there must be a better way to look at this change in EG. And at the end of the day, it is change in EG. Now we know from the definition of work that work is also change in energy. Okay? And that change in energy can also be written down as F times displacement or distance, which equals to the same as F times radius. Okay? Now, as I said before, this is more calculus based, so you are not going to be required to explain how you get this formula. I'm just going to show you how you get this formula, and at the end of the day, we'll work with the final product, but at least you'll know where it comes from. So we know that work is change in energy. Change in energy meaning it takes work for the object to move from its maximum gravitational potential energy to a minimum gravitational potential energy. There was a change in the energy. So there was some work required in moving this object from far away to closer. Now, of course, as we know from universal gravitation, that as I'm closer to an object, my force is larger. So imagine this is R1. And as I'm further away from an object, then my force is smaller, which we know from universal gravitation. It's big G m over r squared. The smaller the r, the bigger the force. The larger the r, the smaller the force. So we're going to talk about how we can figure out this area under the graph, because we are literally moving from one point far away to another point closer in terms of universal gravitation, in terms of gravity. And the question is, since we are moving from one point to another and there is a radius that is involved, so that means there was some work that was required of that object. So we're going to solve this using something different. We're going to change it up. We can't use this formula anymore. So how can we go about doing it a different way? Now the method that I'm going to show you is more calculus based, so don't ask me why I did that, where I got that from. I'm just telling you this is how you do it. And when you do calculus next semester, you might understand it a little more because it had to do with rate of change. Okay? All right. So that is something to keep in mind when you are doing when we are doing these questions. Okay, so we know that to find the area under this curve using calculus, I can use the following formula, and that formula is square root of f1 times f2 times r2 minus r1. That's a formula that is going to give us the area under this graph, which will give us how much work is required to move this object from one point to another. As I said, this is the formula. Where did it come from? All that stuff, don't worry about it. Okay? Alright, so what I'm going to do is I'm going to plug my numbers in, or my values in, and I'm going to end up with the following. It's going to be big G, big M, small m over R1, okay, times R1 squared, of course, times big G, big M, small m divided by R2 squared. And this is R2 minus R1. Okay, what we're going to do is we're going to multiply both sides, and you end up with the following: the square root of big G squared, big M squared, small m squared divided by R1 squared times R2 squared times R2 minus R1. Cool? We're okay with that? Of course, we're going to square root the whole thing, so you end up with the square root of, you end up with big G, big M, small m over R1 times R2 times R2 minus R1. We understand how we did that? Okay. What we're going to do next is we are going to expand it. And when we do, you end up with big G, big M, small m over R1 times R2 times R2 minus big G, big M, small m over R1 times R2 times R1. Correct? Okay, so my R2 and R2 cancel out, my R1 and R1 cancel out, and you're left with the area under the graph, which equals to big G, big M, small m over R1 minus big G, big M, small m over R2. This is the area under the graph. But we know that change in energy, which is work, is actually Eg2 minus Eg1, not Eg1 minus Eg2. It's Eg2 minus Eg1. So if I was going to do that, the way I can write that down, it would be change in energy, which equals to negative big G, big M, small m over R2 minus negative big G, big M, small m over R1. That minus that. Okay? Now what we're going to say is this R right here, R2, let's say that R approaches infinity. Meaning the R is so far away that for all intents and purposes, our energy goes to 0. So now, we are left with just one tiny little section, and that is going to be our new formula. Okay, and from now on, big change in energy equals to big G M over R1. Okay, and from now on, we're going to say that if I want to talk about energy, then my formula is going to be big G negative big G M over R. And you're like, why is it negative? Because that EG right here was negative. That's EG. That is change in EG. As you could see, you're looking at it and saying, how could energy be negative? How could energy be negative? Okay, and I want you to think about this in the following manner. So basically what we're saying is when I'm on the surface of the earth, I've taken energy from which I was supposed to gain when I'm at maximum height, and I've brought it down to earth. How would I describe why it's negative? How could you describe it? Yes. No. Well, it was because I subtracted this minus that. If I subtract it, well, we know that this is negative R2, so it's going to be negative minus, and we know that this is also going to be borrowed energy. That's why it's minus, yes. Energy lost. Well, you're not really losing energy. This is what you're doing, and I want you to think about it in the following way. All right, so when you're on the surface of the Earth, and my rocket scientists at NASA want to send a space shuttle or some kind of rocket into space, they don't just fill up the gas tank and they're like, yeah, we're going to hope to pray to God that somehow that rocket is going to make it to space. That's not what they do. So how do they know what energy you required to put into your rocket? How do they know that? That's correct. You need to know how much energy you need to escape the Earth's gravitational field so that you'll know exactly what energy is required for you to go from one point to another point. So if you think about it, my maximum energy of my whole system is where? At the bottom. This is where my EG is maximum. You're like, how could EG be maximum at the surface? Well, what we're telling you is, think about the energy from the top and bring it all the way down here. This is your maximum energy right here. It's like when you buy a house, you go to the bank, you get a mortgage of $1 million, and now you don't own the house. You're going to pay off the house, and when you pay off the house, The amount of money you